So today we're going to talk a little bit about some imaging sequences. So we're going to talk about so-called spin echo pulse sequences, gradient echo pulse sequences. We're going to have a description of spatial encoding, discuss slice select gradient, frequency and phase encoding, talk a little bit about K-space, which is where all the image data is collected, how that data is collected and processed, and then just describe factors that affect imaging time. So in MRI, there's many pulse sequences that are in use. The two most common would be the spin echo pulse sequence and a gradient echo pulse sequence. The great thing about MR is that just when we think that we've come to the end of what we can do with it, someone will find a new phenomena that we can investigate. And a good example of that is what we now call as susceptibility-weighted imaging, and that's really good for looking at microhemorrhages. So for instance, it's one of the go-to sequences for people that have had mild traumatic brain injury or concussion or blast exposure to blast injury. In head-to-head tests with CT, it's been proven that it's more sensitive at looking at those very small microhemorrhages. Again, my background is as a radiographer, so what I wanted to do was just kind of show you what it looks like at the interface when the radiographer sits down to do a scan. So here I've just kind of pulled down what would be a standard protocol for doing an abdo. So all of these imaging sequences are going to be run in one study. You can see over here an example of what the imaging time is. So you can see here we're doing localizers, we're doing things like coronal breath hold haste imaging, which is a way of doing a very fast spin echo sequence, obviously in 21 seconds, so the patient can hopefully hold their breath for that long. We can do an axial Dixon technique, which is just another fancy way of saying that we're going to look at how much fat and water is in a tumour. And we can do all these other ones like space is just another way of saying that we're doing fast spin echo imaging. But I just wanted you to get a sense that this is all of what we would do in one examination. It's not like we sit down and we go, this is one X-ray, that's another, that's the examination, over and done. So this is the interface where the radiographer sits, and this is what they see. So in clinical MRI, what we're really trying to do is we're trying to get the signal as high as possible, we're trying to get the contrast as high as possible, and we're trying to get the examination time as short as possible. So that's our three trade-offs. So every time we sit down and image someone, they're the three things that we're trying to balance. We can't get the highest signal that we would always want with the best contrast with the shortest examination time. Otherwise, we would, scan about one patient in a day. We're always under pressure, so what we're doing is making those trade-offs in the development of protocols and adjusting them slightly depending on patient presentation, whether they be someone like a child or maybe someone that you think is going to be a bit of a wriggler. You may just have to make some small changes. So the contrast on an MRI image can be manipulated by choosing the pulse sequence parameters. So that's where we can change things like the echo time and the repetition time. So that will allow us to make our sequences more T1 weighted or more T2 weighted to show different things. I always think of the T1 weighted imaging as kind of showing us the best anatomy, and T2 shows us really depicts pathology better than T1 in most cases. And our contrast runs, if we inject contrast, we always do those as T1 weighted sequences after the injection or even during contrast injection. So the pulse sequence sets the specific number, strength and timing of the RF, so our radio frequency pulses that we use for excitation, and our gradient pulses. So they would have been discussed in Lecture 2. So these parameters determine the spatial resolution, the contrast resolution and the contrast mechanism that we want to display. So does everyone understand the concept of spatial resolution, what spatial resolution is? So it's what defines how small a structure we can see. So if our spatial resolution is quite coarse, say 1 centimetre, that makes it very difficult to see a 1 millimetre lesion, and sometimes that's what we're looking for, is a 1 millimetre lesion. So for instance, with breast cancer, we start to think about cancer, things that we want to investigate further being about 3 millimetre or larger. So that dictates what sort of spatial resolution we need to have. Okay? Our contrast resolution is all about if we have two like structures side by side, but they're composed of different tissue types, our contrast resolution is about being able to tell those two things apart. So that's our contrast resolution. Okay, so there's a number of sequences. We use different repetition times and different echo times. So repetition time is our TR, echo time is our TE. We use different TRs and TEs to weight our scans differently. So today we're just going to talk about the two most common spin echo pulse sequence. So it's the most common imaging sequence that you'll see in MR, slightly different variations on it, but the spin echo is the most commonly used. And classically, we think of that as providing a maximum of signal. We can also do gradient echo pulse sequences. So typically these run for shorter. So I showed you on that tree where we were doing some breath hold imaging. So on Siemens scanning, we use a vibe sequence. So obviously we want those to be much shorter. So if we think of our spin echo imaging maybe going for 3 minutes, obviously no one's going to hold their breath for that long. We want to start thinking about doing gradient echo imaging so we can do those in breath hold sequences. Anywhere between, say, or even with the really short imaging sequences, we can do breath holds in 6 seconds, out to about 24 seconds. Okay? So that's where we start to think about just opening up the armoury and saying, okay, we're going to go with gradient echo sequences if we want to do breath holds. So they provide a shorter examination time. They allow for a specific contrast mechanism, that T2 weighted, that T2 star weighted, sorry, and they allow for 3D imaging. So lots of times, say we're imaging a knee, we'll acquire the whole knee in what we call isotropic resolution. So that means that it's the same spatial resolution in all three planes. So if we acquire it in a sagittal plane, we can reformat it as coronal, axial or oblique plane and have the same image resolution. And that's one of the great things with MR, that we can do those sort of isotropic resolutions, reconstruct our images along any plane and still have excellent detail. So let's talk about spin echo pulse sequence. So a spin echo pulse sequence recovers the signal lost due to magnetic inhomogeneity, so therefore minimising those T2 star effects. So an example there might be if we wanted to image someone that's got an implant, say we were doing a shoulder MR, we know they've had surgery, they've got some metal in that shoulder. If we try and do gradient echo imaging there, we're probably not going to see much detail of the shoulder. But if we do spin echo imaging, we're more likely to see a whole lot more of that information. Okay? Apart from the fact that it gives a maximum of signal, there's sometimes when it's just plainly more appropriate than doing gradient echo imaging because we're just going to lose the area of interest. So as I said, minimises those T2 star effects. It's used to ensure that the protons are precessing in phase when the signal is collected, so it gives a maximum signal. It describes the excitation of magnetised protons in a sample. So classically what we think about is we have our RF excitation pulse. That leads to the production of a free induction decay, and then it's followed by a second 180-degree RF pulse to refocus those dephasing spins to form a spin echo. This is what it looks like. So if we think about what a pulse sequence looks like, this is how it plays out. Here's our radio frequency, our excitation, and this is the signal that's generated down below. So we start off here, we look at the application of a 90-degree pulse, and then we look at the application of a 180-degree pulse, which will bring those dephasing spins back to an echo, and here's the generation of our signal. So the things to be that you guys are going to need to know in an exam situation is just this definition here of what the TE looks like. Okay, So basically, here's the application of our 90-degree pulse, and here's the generation of our signal. So that's our time to echo, or TE. And our TR is where we've got a 90-degree pulse and another 90-degree pulse. So that's our repetition time, or TR. If we look into that a little bit further, it just becomes more complicated. But again, you can see our RF down here, you can see our echo down here, and what this is telling us that on top of all this going on here, there's just a few other things that go on about helping us to spatially encode that signal. So we have our slice selection. So remember, we spoke about slice selection before. The way that we encode that signal is that we turn on a small gradient over the top of the main magnetic field, and therefore when we transmit our RF, we only excite one slice. So you can see that that slice encoding gradient is turned on at the same time as the 90-degree pulse and the same time as the 180, so that we're just exciting one slice. Becomes a little bit more complicated when we talk about phase and frequency encoding, and to be honest, on a day-to-day basis, when you're sitting there and scanning, you're not thinking about, whoa, do I need to adjust all these things? It's built into the protocol already, okay? But it's here to show you what's going on under the hood. And then we see the generation of our echo down the bottom. So the echo is what we then read out in our coil, which we then use to eventually have image formation. So let's just walk through those steps. So we have our 90-degree pulse is applied. So that will flip that net magnetisation vector, or the difference between those that are aligned and anti-aligned. We'll flip them into the transverse plane and put those spins into phase. Remember, application of 90-degree pulse, two things happen. We flip them into the transverse plane and they go into phase coherence. So what we're seeing here is, here's our V0, our external magnetic field. Our 90-degree pulse, we flip this magnetisation down here into the transverse plane. And it's in phase coherence at that point in time. Step 2, after the 90-degree pulse is removed, immediately we see a free induction decay. So those signals will start to relax back into the alignment and they'll start to dephase. And they do this because of T1 and T2 relaxation, inherent factors related to the tissue under examination. So T2 decay occurs immediately. So what I'm showing here is that here where we have phase coherence, we will start to see those individual spins fan out. There'll be some that are moving slower and some that are moving faster. And they're doing that because they're chemically different. Those protons are bound to different chemical species. Might be fat, might be water, might be bone, might be a tumour. But they will be different amongst the different tissue types that we're examining. Okay, so T2 decay occurs immediately, causes tissues with different T2 relaxation times to dephase faster or slower. So here's our faster, our slower. Okay, so magnetic moments that slow down will form the trailing edge, that's our S here, and those that speed up will be our fast edge. When we apply our 180-degree pulse, what we do is we then flip all those spins over. So what that is now saying is that the 180-degree pulse will flip these moments through 180 degrees. Okay? So the individual spins, all protons, that is. So the magnetic moments that formed the trailing edge now become the leading edge, and vice versa. The magnetic moments that were the leading edge now become the trailing edge. So at some time that we know, that we can predict, the two edges will be superimposed. So let's just look at this figure down here. External magnetic field, 90-degree pulse. We now flip our magnetisation into the transverse plane, it's in phase coherence. Immediately we will see dephasing. So we have slow and fast, and they're going through this dephasing due to T2 star effects. And here they are fanned out. Once we send in our 180-degree pulse, they flip over to the other side. And if we wait a certain amount of time, they will come back into phase coherence. So when they're in that phase coherence, they've made a spin echo, and that's when we collect our data. So we have a maximum of signal. So here you can see that. There's our magnetisation aligned along the Z plane. We flip it over into the transverse plane, it starts to dephase. And at this point in time, that's the effect of our 180-degree pulse, where we flip them over to the other side, wait the same amount of time, and then suddenly we have a spin echo forming. So does that make sense? Yes?
So when you flip it into the 180 and then they come into phase coherence,
Yes.
do they stay in phase coherence or then they start to spread again?
No. When you flip them over, we don't change the speed, so they're still dephasing, but in a sense they're rephasing, if that makes sense. So if you look at here, you'll see where they're starting to fan out. When we flip them over, then they come back together.
But then they don't like cross.
Well, they would, but we don't. We collect it when it's at a maximum. So we collect it when they come back together into phase coherence. Yes, they will keep doing that until they've completely stood back up into alignment. But we choose when we want to collect that echo time. Okay? And when we collect that echo time is based on the parameters that we set. So if we wanted to do a T1 weighted scan, we will say that our echo time that we want to collect it at is 25 milliseconds. So when you're sitting there as the radiographer and you're saying, I want to do 25 milliseconds, what that's doing is going back to that pulse sequence and choosing how long this time is. Okay, so it chooses how close these pulses are played out. Now that's not something that we characteristically think about when we're scanning, but when you choose that 25 milliseconds, that then goes away and sends that instruction to how the RF is played out, and it's done for you. Okay? So what we're thinking about as the radiographer sitting there scanning is saying, I want to do a T1 weighted scan. These are the parameters that I need to choose. Okay? And if I want to do a T2 weighted, then it's a different set of parameters. Okay? So, important things. The speed and the magnetic moments remains the same, so we're not changing the inherent T1 and T2 relaxation time of the tissue, they stay the same. All we're doing is flipping them so that they will rephase into an echo. Okay? So after the 180-degree pulse, the trailing edge begins to catch up with the leading edge, and that's what I was showing you on that little diagram. At a specific time later, the two edges are superimposed. At this instant, the transverse magnetisation is in phase, so it's in phase again. So we have a maximum of signal induced in the coil. So just going back, looking at that, so flipping, dephasing, 180-degree pulse, and they rephase into a maximum. Okay? So we can't change the T1 and T2 relaxation time, but we can choose at what point in time our echo is collected. And when that echo is collected will be reflective of how much T1 or T2 relaxation has occurred. So that's how we can tease apart our pathologies. And another way to think of it is just, really simple is, if we think of this kind of idea of running around a racetrack, okay? So the starting gun goes off, we have our fast hare and our slow turtle, they run around the race course. At some point in time we say, everyone come back. All right, if we wait for them to turn around and they run at exactly the same speed, they're going to finish this start line at a known point. They're going to finish together because they're running at the same speed. So the one that's run the furthest has got to come back the furthest, and the one that run the shortest has got to come back the shortest. And if they run at exactly the same speed, and we think about our T1 and T2 relaxation time are constants, we don't change them, they're going to come back and be over that line at exactly the same time. That's when we collect our echo. Okay? And again, just that idea, our 90-degree pulses are applied, they head off down a track. At some point in time, we call them back. We wait a certain amount of time, and then they'll come back to that start line at exactly the same point. They'll be crossing that starting line at the same point in time, and that's when we collect our echo. Okay? And again, just those definitions, our TR, or time to repetition, is the time between each 90-degree pulse. So here's our first one, here's our second one, so that's our TR time. Echo time is the time between the 90-degree excitation pulse and the collection of the spin echo. Okay, so that's our 90-degree pulse, there's the collection of our echo, and this tau time is when we send in our 90-degree pulse. Remember I said if everything stays constant, we send in our 180-degree pulse and then we wait in a certain amount of time. So we wait the same amount of time between the 90 and the 180. If we double that, that's when we collect our echo. So that first point between the 90 and the 180 is our tau. All right? So when we think about doing our spin echo imaging, I've already mentioned before that we don't actually measure true T1 and T2 and proton density. We collect T1 weighted, T2 weighted, or proton density weighted. The reason that we don't collect the pure image is it would take too long. So we just want to weight it towards that. So what that means is that we want to limit the contribution of one contrast mechanism and maximise the other. So what we think about is the TR controls our T1 weighting, and it does this. So a short TR maximises our T1 weighting, and a long TR maximises our proton density weighting. So when I said that when someone comes to you, a radiologist says, I want you to do a T1 weighted scan, you're immediately going to think, I want to do a short TR scan. Okay, and our TE controls T2 weighting, long TE maximises T2 weighting, and a short TE maximises proton density weighting. So if someone says, I want you to do a T2 weighted scan, you're automatically thinking I need a long TE, and if I want to minimise the contribution from TR, I want it to be a long TR. Okay? If I want to minimise the contribution from T1 weighting, I want to make it a long TR. So a T2 weighted scan looks like long TE, long TR. And a T1 weighted scan looks like short TE and short TR. In proton density weighting, you want to minimise the contribution from both, so it's a short TE and a long TR. Make sense? Any questions? Okay. So gradient echo imaging, as I mentioned before, is another common imaging sequence that we do, except this time we don't use that 180-degree pulse. We manipulate the formation of the gradient echo by manipulating the gradients, by basically using the gradients to speed up and speed down our protons, our dephasing protons. The reason that we want to collect gradient echo imaging might be that it has a shorter examination time. So if we want to do breath holds, we don't want to have someone hold their breath for 3 minutes. We want to do it more like 20 seconds. So we're going to do gradient echo imaging. The other thing that we see differently is that it uses an excitation pulse that's variable. So before, where we were talking about a 90-degree pulse, it might be different than that. So it will use a excitation angle that we'll refer to as theta, but theta can be anything from 1 to 120 degrees, depending on what contrast mechanism we want to make, and also depending on how fast we want to image. But the key point is it flips that magnet, that net magnetisation, through the angle that we apply. So it no longer goes 90 degrees, it might only go 15. So automatically we're not as affecting as many spins. when the flip angle, when we use a flip angle other than 90 degrees, yeah, as I said, we don't flip it, all of it into the transverse plane. We only take a small amount, okay? So the signal strength will be less than a spin echo. So gradient echo sequences, if we run them side by side, if I go and do a gradient echo sequence through a brain, and I do this exactly the same slice with the spin echo sequence and measure the signal to noise ratio, it will be substantially higher with the spin echo sequence. But there may be reasons why we're doing it, and one of those is shorter examination time. So how does it look? So again, looking at step one, we have our RF excitation pulse applied with a known angle. As I said, that angle might be 15 degrees. So we're going to flip them 15 degrees towards the transverse plane. Again, once that RF pulse is removed, we see a free induction start to decay away. T2 dephasing occurs. Step 3 is, rather than send in a 180 degree pulse, we're now just going to form that gradient echo by manipulating the gradients, by making those spins speed up and speed down so that we can form a gradient echo. And because we're not applying that 180 degree pulse, we don't have to wait for the time to apply it. We also don't have to wait for the amount of time for them to flip over and come back into phase coherence. So we can save time. That's why it tends to be a faster examination. So gradient field is applied. Remember we spoke about gradients before, so that's our X, Y and Z gradient field superimposed over the main magnet. So we turn those on in a known way to speed up and speed down the protons. So they will rephase very similarly to what we saw with the 180 degree pulse until we get the formation of a maximum, our gradient echo. Okay? And again, important things to note. Again, we're not changing the inherent speed of the dephasing. We're not changing those T1 and T2 parameters. We're just changing the speed of the protons, the way that they, in a known way, how fast they are travelling. But we're not changing the T1 and T2 relaxation times. So at a specific time later, the two edges will be superimposed, very similar to what we saw with the gradient echo technique. Okay? And at that instance, again, we have the maximum signal in the transverse plane, which induces a voltage in our coil, and that's what we collect. The collected signal, in this time being a gradient echo, typically has lower signal to noise ratio than a spin echo sequence. So remember before I said that if we collected the same slice in a brain with a gradient echo sequence and a spin echo sequence, the gradient echo will have significantly less signal to noise ratio because of the way that we've collected it. We haven't collected the maximum magnetisation. But as I said, there's reasons for doing that, and some of those revolve around speed and the need for three-dimensional imaging. So again, just looking at those definitions, here's our TR. Our TR is the time between those excitation pulses. The TE is the time between the excitation pulse and the collection of the echo. And our tau, again, is just that point in time where we say, here's our excitation pulse. Now I'm going to apply rephasing to collect that gradient echo. That's our tau, and at 2 times tau, we'll have a gradient echo collected. So advantages, gradient fields rephase quicker than the 180 degree pulse, which means we can go faster. We can have a shorter TE and a shorter TR, so that again just goes back to this idea that we can do it faster. Okay, we can image faster, we can have a slightly different contrast mechanism. Disadvantages is that there's no compensation for that magnetic field inhomogeneity. So our T2 weighting is now really T2 star weighting because we haven't compensated for those inhomogeneities. And remember, those inhomogeneities can be inherent in us. Areas where we have soft tissue next to air will give you inhomogeneity. Areas where we've got metal implanted inside the body, whether it be a prosthesis, surgical clips, or even things like metal braces will give us inhomogeneity, so we can't correct for those as well. We tend to have smaller signals, so we have smaller signal to noise ratio. We can still weight our images towards these T1, T2 and proton density weighted. And again, these are the parameters which will allow us to create T1, T2 or T2 star or proton density weighted images using a gradient echo technique as opposed to a spin echo technique. So again, we're looking at short TR, short TE. Okay, a longer TR, a long TE, a long TR, short TE, but this time we can also help that weighting by manipulating the flip angle. So that's that excitation flip angle. Any questions? Just remember, they're the two main sequences that you will encounter. Okay, just going to talk a little bit about image formation. So hopefully we all remember axial, so carving up from head to foot, coronal, carving up from front to back, and sagittal, carving up from side to side. So remember, one of the great things about MRI is we can scan in any plane. So on CT, you put a person on a table, you push them through the imaging gantry, and you basically slice them up along the body. There are a few variations. You can get close to doing direct coronals, say for facial bones. If you put the patient on the table, on their abdo, head extended, angle the gantry, you can get close to doing some sort of direct coronal imaging. But that's about the limit with CT. On MR, all we do is we manipulate how we do our slice select, and that will tell us if we're doing direct, transverse, sagittal, coronal, or a combination of those to do a true oblique imaging. So let's just go back to the beginning. Remember our Lamar equation: precessional frequency equals gyromagnetic ratio times magnetic field strength. Okay? So if we think about that, that will give us the precessional frequency of protons. So the thing that we can control as radiographers is B0, that magnetic field strength and the strength of the gradients. And again, we're not sitting there saying the gradient strength is going to be X, Y, or Z milliteslas. The machine does that for us. But in a way, we control it by saying how thick our slice is going to be and how fine our matrix is going to be. Okay? So the Lamar frequency states that the resonant frequency is proportional to magnetic field strength. If the main magnetic field strength is uniform across the sample, all protons in the sample will have the same frequency. So in an ideal world, if I put any one of you in an MRI scanner and I transmit RF at a certain frequency, I could potentially excite every proton in your body at once. And then when I read those signals out, I'd get lots of signal, but I'd have no idea where it came from in the body. So what we need to do imaging is we need to spatially encode where those signals came from. And if you look at the sort of history behind MR, 2 Nobel Peace Prizes were given for the invention of MR. One was the recognition that different tissue types had different T1 and T2 relaxation times. So therefore we could tell the difference between normal tissue and cancer. The other person that got the Nobel Peace Prize was a guy that came up with the idea of how to actually work out where those signals came from. Okay? So that was his contribution to say that if I add gradient fields and I do spin echo sequences, I can actually tell you where that signal came from. So no, not only can I tell you about what's cancer and what's not, I can actually tell you where it is within the body, which is kind of helpful if you want to treat it. So how does that work? If a gradient magnetic field is applied at exactly the same time, so superimposed over the main magnetic field as the RF pulse is applied, then we've suddenly excited a single slice within the body. Okay, so the resonant frequency of the spins becomes spatially dependent. So if I put someone in the scanner and I landmark them at their umbilicus, so if I move 1 centimetre superiorly or 1 centimetre inferiorly from the umbilicus, it has a different magnetic field at that point in time because I've changed the gradient from head to foot. So therefore, if I transmit RF, I can excite a slice 1 centimetre above, 1 at the umbilicus and 1 centimetre below. So again, just showing if that's our isocentre. So what happens when we put someone on the table is we pick a centre point. So if we're going to scan someone's brain, the centre point is the glabella. So we put them in the scanner, we turn a laser light on, we move them through to that laser light being on the glabella. We get that's our centre point, then we push them into the scanner. That then becomes 0. This is all positive, this is all negative. Does that make sense? So then we know that's our isocentre. Everything up here, if we apply a gradient, will have positive, if that makes it, if I'm just simplifying by saying it's a positive, and this becomes a negative. So what I'm saying is that if it's 64, at an extreme this becomes 68, and this becomes 60. So I've added 4 and taken away 4. So then I can say that if I fire RF, which relates to this 68, then I'm only going to excite these ones here versus these ones versus these ones. Okay? So it's the fact that we've got a gradient superimposed over that field. And depending on how strong that gradient is, will dictate as to how thin our slice is. So the stronger the gradient, the thinner the slice. There is a limit. We can't make those gradients too strong, or we'll give the patients a lot of bioeffects, and those bioeffects will be things like peripheral nerve stimulation. So the muscles will start jumping because we're changing those gradients on and off very rapidly, and we're inducing a current in their peripheral nerves. You can probably come across that when you do your safety assignment. So the gradient magnetic field is much weaker. So when we talk about our MR scanner being in terms of Tesla, so we talk about 1.5 Tesla or 3 Tesla, those gradient fields are in milliteslas, so much weaker. However, it's strong enough to create a range of resonance frequencies in the direction of the gradient. So if we're applying our gradient from head to feet, we're changing it in a known way. So if the helper gradients, the spatial location being excited can be limited. So we only excite, a slice 1 centimetre above the umbilicus, which is 5 millimetre thick, based on the resonance frequency. So gradient excitation methods can be used to receive information on points, lines, spaces and volumes. All that's saying is that we can collect our data in different ways. Okay, gradient fields are generated by a set of coils positioned perpendicular, so at 90 degrees to one another. So remember I said that if we think about putting someone in the scanner, the main magnetic field runs from their feet to their head. Okay, then we have gradient coils in the X, Y and Z direction. So ones that can change it from head to feet, ones that can change the magnetic field from left to right for sagittal imaging, and ones that can change it from front to back for coronal imaging. So we have 3 sets of gradient coils. So they can vary the field in the X, Y and Z directions. So the system is then able to locate the signal spatially in 3 dimensions. So now I can not only say that I can tell the difference between normal and cancer tissue, I can also tell you where it is within the body. I can say it's within the right lobe of the liver versus somewhere in the body. And these gradient coils, we talk about them performing that slice select. So that's where we turn them on at the same time as we fire in our RF, so we're just selecting an individual slice. Then we just have to locate it in the X and Y direction, and we do that by phase encoding and frequency encoding. So just again to show you that's what it looks like. Here's our patient within the imaging bore. So we have this coil and this coil from head to foot so that we can change that gradient field from head to feet. We have one on either side of the patient, so we can change it from left to right for sagittal imaging. And we have one at the front and one at the back so that we can change it for coronal imaging. And if you want to get more complicated, we can change 2 sets or even 3 sets to do true oblique imaging, which is really good. Say you're doing a shoulder scan and you want to look at the rotator cuff, which runs at an angle in the body. We do our localizer, we'll work out where our rotator cuff is, and we just swing our acquisition around and collect true coronal imaging of the rotator cuff by energising 2 sets of coils. So how does it do it? Again, we're just thinking about what sort of imaging we want to do. Are we doing sagittal, coronal, axial? The axes in which the gradient acts depend on the plane being imaged. So what that's saying is that if we want to do an axial image, then we're talking about changing it from head to feet. Okay? So we're talking about changing the coils at the top and the bottom of the body, superior, inferior extremes of the body. So if we turn that on, so because we can do this in multiple planes, the example I'm going to use is just talking about making an axial image. The sets of coils that I'm going to mention obviously change depending on where we're doing true sagittal or true coronal, but for this example we're just going to talk about axial. So first we want to locate a slice, so we want to change that gradient from head to foot, so we can just do an axial slice. So we have our slice select gradient being from head to foot. Once a slice is selected, the signal is located or encoded along both axes of the image. So what I'm saying is that once we carve that up into an axial slice, we then just need to know where it's coming, where the signal's coming from a coronal perspective, from front to back, and from a sagittal perspective, left to right. So this is how it looks. Here's our patient. We're changing the current between here. So here's our z-axis, here's our y-axis, and here's our x. So we're just talking about there being 3 different sets of coils in place. And depending on how we energise them, that's what we're going to see. So if we're doing a slice select, when the gradient coil is switched on in the z direction, so that's our z. And remember, the example is in an axial. The magnetic field strength and therefore the precessional frequency of nuclei along its axis is altered in a linear fashion, so in a fashion that we know. So B0 in the resonance frequency is smaller at the feet and larger at the head. Okay, so if we think of that again, if we think of this as sort of being a negative and this being a positive, it's smaller here and larger here if our ISO centres through the middle there. Just think about that example of the umbilicus. Yep, so we've now changed it in a known fashion. So a slice situated at a certain point along the axis experiences a different magnetic field strength. So it experiences the B0, which is our magnet, plus or minus the gradient strength, depending on whether it's superior or inferior to what we selected as our ISO centre. So it has a different precessional frequency, depending on how far along the table it is. And again, if we just think about it, here's our gradient being superimposed. So at slice A, we've got this frequency, and at slice B, we've got a slightly different frequency. So if we transmit RF related to that frequency, we just excite that slice. If it's transmitted at a different frequency, then we excite that slice only. Does that make sense? Okay, and again, just showing you how that looks. So there's our slice to be imaged up the top there. If we transmit RF, which equates to that frequency, we're only going to excite a slice in the patient's brain. Okay? As I mentioned before, there's 2 ways to change the thickness of that slice. We can have a different excitation bandwidth. So we don't transmit a pure frequency, it's a bandwidth of frequencies. So the bandwidth of frequency will tell us how thick the slice is, 10 millimetre, 3 millimetre, 1 millimetre or 0.5, just depending on what we're looking for. And we can change the slope of the gradient, so we can make the gradient stronger. Remember I said there's a limit to how strong we can make that gradient before we start to have bioeffects. So the patients start to experience peripheral nerve stimulation. Photoscintillations, people that get imaged at 7 Tesla are in the scanner, eyes closed, and they've got flashing lights in their eyes because we're interacting with the conductive pathway to their optic nerve and their visual centres. So obviously we can't make that too strong, or we can give them permanent side effects. The slice is excited by transmitting RF at the centre frequency corresponding to the precessional frequency of nuclei in the middle of the slice. So that's the idea of that bandwidth. We pick the centre of the slice, we transmit frequencies slightly different either side if we want to, depending on how thick we want that slice to be. But the nuclei, the important thing is that nuclei in the other slices along the gradient, they're not at the same resonant frequency as the one that we've selected, so therefore the RF doesn't flip them into the transverse plane, okay, because they're not on resonance. So the RF bandwidth and the gradient slope determine the range of nuclei that resonate on either side the centre, essentially how thick or thin the slice is. Okay, so as I said, now that we've excited a slice, we now need to know within that slice where the signal's coming from. So if you can imagine, you know, we've got a sheet of paper, we've excited that whole sheet. Is my signal coming from the front of the sheet, to the left of the sheet, or from the right of the sheet? So we use phase and frequency encoding to do that, okay? So it just becomes another way of sort of encoding the signals, but rather than using radio frequency pulses, we're now just going to use manipulations of gradients. So the signal must now be spatially encoded, located along the coronal axis of the image. And again, we're using that example of axial imaging. And we do that by a process we call phase encoding. So all the magnetic moments along the axis are originally at the same phase. Okay, when phase encoding gradient is switched on, we can speed some of them up and slow some of them down, depending on how strong we make that phase encoding gradient. So therefore, the precessional frequency along the coronal axis of the gradient is altered. So again, with our higher frequency, we speed them up. With our lower frequency, we slow them down. So this changes the phase of magnetic moments from front to back. And again, remember we're using that axial imaging example. So we're changing the phase from the front of the body to the back. When the gradient is switched off, we've manipulated the precessional frequencies of those individual protons. And then we can use that information, that frequency information, once we collect it, to impart spatial localization into our image. Okay, so they're still rotating, they're still precessing, they're still recovering their magnetisation or the decay based on their T1, T2 parameters. It's just that we've manipulated them so that they will give us information about their spatial location. So again, if we just think about changing it from front to back, all that's happening is we're making some precess faster and some precess slower. But we've changed that in a known way so that we can unravel that information and basically work out our image. So just again, showing you how that looks. So if we think of all our individual moments as being in phase, if we make this stronger at the front and weaker at the back, you can now see that we've imparted a known change so that we can then read out that frequency. That frequency will then tell us where their spatial location is within this matrix, this very coarse matrix that we've used here. So that's a matrix 4x4. When we do this imaging, we might be doing 512 steps times 512 steps. But that is what allows us to work out what's going on, to work out where they come. So that's phase encoding. We can do the same in the other direction with frequency encoding. So the signal now has to be located along the sagittal axis. So we've done front to back, now we need to do left and right. Remember, we've got our 3 sets of gradients. So all we're doing is changing the current in another set of gradient coils. Those X, Y, and Z ones. So we're changing it in X for one part of imaging, we're changing it in Y for another, and then in Z for another. So that's how we're getting our location. So using that example of axial imaging, if we now switch on our X direction, we can change the frequency of those protons from left to right. So we can induce a frequency shift under the influence of that gradient. So the signal can now be located along the sagittal axis by using that gradient encoding. Okay, so the columns of pixels from left to right are therefore discriminated in terms of their frequency differences. So how does that look? Here's our cross-sectional image. We've got our gradient turned on, and you can see that we have slightly different frequencies at different points, spatial points within that image. So if we read out these frequencies, we can now say where that image is located within that one slice that we excited. And again, if we think of left to right, you can see that they have slightly different phases and different frequencies now. Okay? So if we think of here's one slice, here's one encoding step down to 256, you can see that we've got very slight differences in the frequencies. So MRI is all about, when we collect that data, about collecting that frequency information, putting it through a mathematic algorithm called a Fourier transform, which will nicely decode those frequencies into pixel intensities. But those pixel intensities will be represented based on their spatial location. So the application of the gradient selects an individual slice, so that's our slice select, produces a frequency shift and a phase shift in the 2 other directions. So that's how we get our 3-dimensional location. So the system can now locate an individual signal within the image by measuring the number of times the magnetic moment crosses, or that recovery, how many times that crosses our receiver coil. And this information is now translated into the image. Okay? Probably the only thing else to know about this is just when they're played out. The important thing to remember is that slice select comes on at the same time as our excitation, RF, and our 180-degree pulse if we're doing Spinnaker imaging. Phase encoding is a very similar process, except that we're just manipulating the gradients to change phase and or frequency, depending on which one we're doing. So the phase encoding is recorded after the phase encoding gradient has been switched off, so we collect that signal, and the same with the frequency. Okay, so just to show you what it looks like, if you can imagine that we've excited a slice, so let's, in an ideal world, that if we've excited a single slice and all those protons are exactly the same. So see how they're all precessing at exactly the same phase. So they all look very similar. If we turn on a phase encoding gradient, I've now got this column all travelling at the same speed. So I can now pull this image apart into 3 different columns. So if I turn another gradient on, I've now turned this one, where they all look the same, from columns into columns and rows. Okay, so that's what we're doing. We're turning our phase and frequency gradients on, so that we can now, at any point in time when I collect that echo, I can say this this pixel here, so we think of this as being our image, our acquisition matrix. I can then think of that pixel there having a very particular phase and frequency. And knowing that, I can put it within a point within that matrix. Okay? So now that we've discriminated all of them, you can see here that they all look, from here where we've got 9 that all look the same, we've now got 9 that have got very different characteristics by turning on our phase encoding gradient and our frequency encoding gradient. And another way that I think about it is that if I was to have everyone in this room sing a repetition song, so row, row, row your boat, and I start at the front and I say, I want you to start singing that now, and then I'll wait a small amount of time and say, the next row I want you to start singing, and the next row I want you to start singing. At any one given point in time, I can say, what's the next word you're going to sing, and I can put you within a row within the room. So if I then asked one side of the room to sing with a different pitch and slightly vary that pitch across the room, at any one point in time I can ask someone within the room what's the next word they're going to sing, at what pitch, and I can now say that you're sitting in that seat there. And that's essentially what we're doing with our slice select, phase encoding and frequency encoding. We're finding a way to represent an individual pixel within a matrix where that sits within the body. Does that make sense? Any questions? Okay. Data collection and image formation. So when we're talking about all these phase and frequency changes that we've imparted and collecting that signal back via our coil, all that frequency information now comes into an area that we refer to as K-space. So let's think of K-space as something like RAM on your computer. It's where you capture that information, hold it temporarily until you put it through a Fourier transform, which takes all that frequency information and turns it into a pixel intensity, which we see as grayscale on an image. So when data from each signal position is collected, the information is stored in an array processor. So all that's saying is that we collect a lot of data fast. So we put it into an array processor so it can be reconstructed in a timely fashion so we put it into an array processor of the system until the scan is over. So to put it into terms, there's some spectroscopy imaging sequences that you can run where one run in a patient generates 1.9 gig of data. So we need to collect all that 1.9 gig of data really rapidly, put it in an array processor, and then turn it out into an image as close to real time as possible so that we're not waiting around to start the next scan. So we refer to this storage space as K-space. We think about that as having some specific parameters, a spatial frequency domain. We think about it as being rectangular in shape, with the phase axis being the horizontal and the frequency axis being the vertical. It doesn't correspond to the image. So if I look at K-space and I look at the top row of K-space, that doesn't equate to the top row of the image. We need all of that space together, all of that space reconstructed together. That information in K-space gives us an image. If we get an artefact in that K-space, it impacts on not just one slice, but the whole data set, which is why when you're doing MR imaging, if someone moves during the acquisition, it can toast the whole imaging run. Whereas on CT, you might do an imaging run and they move for one slice, you can go back and repeat one slice. That's not the case with MR because all of that data in K-space contributes to the image because it's got frequency information in it. And we unravel that frequency information to give us an image. And this is what it looks like. If you could go and make a picture of what K-space looks like, that's what it looks like. It's all about frequency domains. We apply a Fourier transform directly to this K-space, and that's what we get, our image. The important things to know is just that the centre part of K-space will give us information about contrast, and the outer parts of K-space will give us information about spatial information. And this is something that you can do. You can actually go and get this K-space. You can do what's called an inverse Fourier transform, and I've done this in places where I've worked as an exercise. You see a little artefact in here, you go into K-space, remove that artefact and recover the image. It's not easy to do, but it can be done. So again, just as I said before, frequency axis, phase axis, these are our individual lines of K-space. But we need to fill all of that K-space out for our scan to be finished. So if we're running a scan for 6 minutes and we terminate it before that 6 minutes, so we haven't filled out all the K-space, we're not going to get an image. We need to fill out all the K-space to have an image. So during each TR, so that time to repetition, the signal from each slice is phase encoded and frequency encoded. A certain value of frequency shift is obtained according to the slope of those gradients. Remember before I said about, umbilicus, superior, inferiorly, think of one being positive, one being negative, so depending on how we've encoded it. So the slope of the the frequency encoding gradient will determine the field of view. So the stronger the gradient, the smaller the field of view. So our field of view might be to image the whole body. It might be a 48 centimetre field of view. We want to image a substantial part of the chest and abdo. But it might be as small as 6 centimetres. 6 centimetres, you might just be wanting to look at a very small part of the brain. So for instance, we might be looking at the pituitary fossa. So we do a 12 centimetre field of view and just concentrate on that area. So that's governed by the strength of the gradients that we apply. So the field of view remains unchanged during the scan, but we can manipulate that field of view by changing our gradients. That's the important thing to realise. So a certain value of phase shift is obtained by changing that phase encoding gradient. So again, depending on how many steps we want in that acquisition matrix will depend on how many phase encoding steps we do. And again, it's changed by changing the slope of it or the strength of that phase encoding gradient. And again, in order to fill out different lines of K-space, we need to change that in a known way. So we need to step through the image. So in order to finish the scan or the acquisition, all of the selected lines of K-space must be filled out. So the number of lines of K-space that is filled is determined by the number of steps that we walk it through. So if we want to make 128, our acquisition matrix that we talk about is 128 by 128, so that's how many pixels we have. So we have 128 in this direction, 128 in this direction. We need to step through that 128 phase encoding steps. And that becomes important because that helps us to determine the acquisition time. So every TR, every repetition time, each slice is frequency encoded and phase encoded with a different slope of the phase encoding gradient. Once all the lines of K-space have been filled, the acquisition is over and the scan's over. So we then get all that data that we've collected into K-space and put it through a Fourier transform. So the recorded signal is measured as a relationship of its frequency against time. Okay, so then the fast Fourier transform converts this into an amplitude of individual frequencies. So once we do that, we can start to assign pixel intensities. So again, if we just think about our matrix, so this is a rather coarse matrix, 8 by 8, but if we think about it, it's annotated by these numbers. We've got 8 in frequency steps. We've got 8 frequency encodes. That will give us our matrix. So you'll hear people say, I want you to go and do a T1 weighted scan with 256 by 256 matrix. So that's giving you as the radiographer a description on how you're going to take the scan. So the number of frequency encodings is taken, so that's our X, our phase is our Y. So if we look at that, that will tell us what our matrix is. And the way that looks is, you know, if we just think about how that, we've now taken our phase, all our frequency information, and we've now assigned it as a pixel intensity. So again, you know, this is 4 by 4, that's a rather coarse matrix and would, you know, not be done. But if we think about making that a very fine matrix, you can now start to see that how these greys, blacks and different shades of grey then represent our image. Okay, so the finer number of steps, frequency encodings, phase encodings will give us how much spatial resolution we acquire in our image. And that spatial resolution tells us about how fine an image, how fine a structure we can see. Okay? All of that is really just leading into this equation down here, which is how we work out scan time. Okay, so remember I said before, ideally we want to scan with a maximum of signal to noise, with a maximum of contrast resolution, with as fine an image as possible in as short a time as possible. It's a trade-off. So the way that we work that trade-off is our scan time. So the maximum number of slices that can be selected and encoded depends on the length of the TR, so depending on how much time we've got to do that. Longer TR allows for more slices to be selected. Okay, so characteristically we can do more slices with a long TR. So it's saying here if we have a TR of say 500 milliseconds, we can get about 12 slices. If we had a TR of 2000, we might get 18 slices. But the important thing here is just this scan time equation. So the way we work out how long a scan takes is we look at the repetition time times the number of phase encoding steps times the number of acquisitions. So when I said before that a T1 weighted scan of the knee might take 3 minutes, that's because we have a certain TR period to excite and then collect our echo. We've got to march through that knee a certain number of times. That's our phase encoding steps. And this next is really the other thing that we quite often do to increase our signal to noise ratio is we fill out case space more than once. So we refer to this as number of excitations. So that's where the next comes in. So the phase encoding gradient is altered every TR period, so we have to walk through every period. The number of phase encoding steps will determine that scan time. So here it is down here, our number of phase encodings. Okay, so that's the important thing to know, you know, for your examinations is just how to calculate this scan time. TR, phase encoding steps, number of necks. And as I said, scan time is also affected by the number of times that the signal is collected. So what we can do is we can fill out case space more than once. If we want to increase our signal to noise ratio, say we're looking at an area of the body that has inherently low SNR, say we're looking around the lungs where there's not a lot of protons, there's a lot of air, we might do a multiple neck scan. And that's a way to increase the signal to noise ratio of the examination. Fill case space out multiple times. Okay, the higher the necks, the more data is stored in case space. Okay, and when we therefore go and do our Fourier transform on that case space, that governs how bright the pixels are within our matrix. Okay. Any questions? Still got, I can still hang around for anyone who wants to come down and ask questions on a one-on-one basis.